Now, how to find out order of the reaction? First method is integration method. We have the expression which is called integrated rate law for first order reaction, for second order reaction. So we put the values with the help of which we determine with the help of experiments, and the case in which value of K comes out to be constant, that is taken as the order of reaction. For example, if the values fit into the expression for the first order reaction, we say that the K or the reaction belongs to first order. And if the values by putting the values in the second order expression we get K constant, we say that the reaction is of second order. But this is hit and trial method. Next we are taking graphical method. In graphical method, for zero order reaction, when we plot the concentration versus rate, as the concentration changes, the rate does not change. Means the rate of reaction is independent of the concentration of reactants. Why it is so? Because zero order reactions are usually very fast. For example, all photochemical reactions are zero order reactions. So they are completed within fraction of seconds. So after that, if we increase the concentration of reactants, the rate of reaction will not change. Next graph is for first order reaction. And first order reaction, the rate of reaction is directly proportional to the concentration. This is second order reaction where rate of reaction is directly proportional to square of the concentration of the reactant. For third order reaction, rate of reaction is directly proportional to the cube of the concentration of the reactants. Now the time required to complete a definite fraction of concentration will be T1 by m. 1 by m may be T half, T1 by 3, T1 by 4, T 99%, T 90%, T 60%, etc. T1 over T2 will be equal to A2 over A1 raised to the power n minus 1, where n is order of reaction. T1 and T2 are the same fraction of time for which corresponding concentrations are A1 and A2. Isolation method or initial rate method. This method is used when more than one reactants are involved. Here what we do, we keep the concentration of one of the reactant constant and find out that how the rate varies by changing the concentration of the other reactant. For example, concentration of A is kept constant and we make the concentration of B double. If rate becomes double, it means the order of reaction with respect to B is 1. Similarly, by keeping the concentration of B constant, if we find that doubling the concentration of A, the rate of reaction does not increase, it means the order with respect to A is 0. Next, we are taking the influence of temperature on reaction rate. The rate of reaction in general increases with the increase in temperature because kinetic energy of the molecule increases and more number of molecules undergo effective collisions. Hence, rate of reaction increases. Effective collision means those collisions which lead to the formation of product molecules. Temperature coefficient tells us how much rate of reaction will increase by increasing the temperature. If we determine the rate constant at 308 Kelvin, ratio of rate constant at 308 Kelvin and 298 Kelvin, or 10 degree higher temperature and 10 degree lower temperature, it is called, this ratio is called temperature coefficient. The rate of reaction generally doubles or sometimes triples by each 10 degree rise in temperature. Therefore, this temperature coefficient for most of the reaction lies between 2 and 3. The quantitative relationship between rate constant, temperature and activation energy was given by Arrhenius equation. That is, K is equal to A e raised to the power minus Ea over RT, where K is rate constant, A is Arrhenius constant or frequency factor or pre-exponential factor, and it mainly depends upon collision frequency. R is gas constant, E is the base of the natural logarithm. Ea is activation energy. Now we are plotting a graph between log K versus 1 over T. This will come out to be straight line with a negative slope. Slope will be equal to minus Ea over 2.303 R. So if you are given the slope of the straight line and you are asked to find out activation energy, this formula can be used. Value of R you will substitute as 8.314 joules per Kelvin per mole. Taking the log of the above equation, we will get log K is equal to log A minus EA over 2.303 RT. With the change in temperature T, the value of log K varies. So the above equation represents a straight line shown here in the graph. If the rate constants are taken as two different temperatures, that is T1 and T2 respectively, for the reaction, the EA, that is activation energy, always remains constant. Log K1 is equal to log A minus EA over 2.303 RT1. Log K2 is equal to log A minus EA over 2.303 RT2. Subtracting 3 from 4, we get log K2 over K1 is equal to EA over 2.303 R into 1 over T1 minus 1 over T2, which is equal to EA over 2.303 R T2 minus T1 over T1 T2. The lesser the value of activation energy, the more easily that reaction will take place and the faster the reaction will be. Now we are explaining this activation energy with the help of diagram. This diagram is called potential energy diagram. Here we are plotting the graph between progress of reaction and energy. HR represents enthalpy of reactants. HP represents enthalpy of products, and the difference between HP minus HR will give you delta H. First graph is for endothermic process. Why it is endothermic process? Because HP is greater than HR. EAF represents activation energy for forward reaction. EAR represents activation energy for reverse reaction. Threshold energy is the minimum energy which reacting molecule must possess in order to undergo effective collisions. Effective collisions are those collisions which lead to the formation of products molecules. Only those molecules can undergo effective collision which have activation energy and they collide in proper orientation. That is, they cross energy barrier as well as orientation barrier to undergo effective collision and lead to the formation of product molecule. The second diagram we have shown you for exothermic reaction. Now why it is exothermic reaction? Because HP is less than HR. EAF is activation energy for forward reaction. EAR is activation energy for reverse reaction. And delta H is enthalpy of reaction, which is equal to HP minus HR. The colliding reactant molecules must possess certain amount of minimum energy to break the bonds or to make the collisions effective, and this is known as threshold energy. Normal molecules have lesser energy than threshold energy. The additional energy required by the molecules to attain threshold energy is called activation energy, which is acquired by molecules as a result of interchange or exchange of energies during collisions or by heating. Hence, activation energy is equal to threshold energy minus average energy of reactants. Now we are going to take up how catalyst increases the rate of reaction. Catalyst increases the rate of reaction by lowering down the activation energy. The top curve represents the reaction path without catalyst, whereas the bottom curve represents reaction path with catalyst. Threshold energy and activation energy is higher in the first reaction without catalyst, whereas in presence of catalyst, activation energy has decreased to EA1. Without catalyst, the activation energy for forward reaction is shown on left hand side and activation energy for reverse reaction is shown on right hand side. And when we use catalyst, you can see that the now activation energy has become EA1 for the forward reaction, and for backward reaction or reverse reaction the activation energy has become EA3. And the amount by which the activation energy is lowered is represented by EA2. It means that catalyst lowers down the activation energy both for forward as well as backward reaction. That is why that in reversible reaction, catalyst does not affect delta H, delta G, delta S and equilibrium constant K. Only it helps in bringing the equilibrium faster. It increases the rate of both forward as well as backward reaction equally, and the equilibrium is attained faster in the presence of catalyst. Now we are going to take up mechanism of the reaction. The series of steps of chemical reaction is called mechanism of the reaction. For example, the reaction between H2 and I2 to form HI was originally postulated as simple one-step reaction. But nowadays it has been proved that it takes place in 3 steps. H2 plus I2 reversibly gives you 2HI, and rate is equal to K into molar concentration of H2 into molar concentration of I2. The first step is fast, that breaking of I2 molecules into 2 iodine atoms. One of the iodine atom combines with H2 to form H2I, which is a unstable intermediate. This reaction is also fast. And in the third step, H2I, which is unstable, combines with I atoms to form 2HI, and this is slow step or rate determining step. Overall reaction is H2 plus I2 gives you 2HI. We are taking the next reaction between NO and Br₂. It is known to be second order with respect to NO and first order with respect to Br₂. How we can prove with the help of mechanism? The reaction is NO plus Br₂ gives you NO-Br₂. Reversibly, this is the first step of the reaction. NO-Br₂ reacts with NO to form 2NO-Br. It is slow step and rate constant is represented by K2. Overall reaction is 2NO plus Br₂, rate constant K equal to 2NO-Br. The rate determining step involves one molecule of NO and one molecule of NO-Br₂. Thus, the expected rate of reaction should be rate is equal to K2, which is the rate constant, into molar concentration of NO-Br₂ into molar concentration of NO. However, NO-Br₂ is a reaction intermediate and its concentration can be calculated from the first equation. K1 is equal to, which is equilibrium constant, equal to molar concentration of NO-Br₂ divided by molar concentration of NO into molar concentration of Br₂. Now from here we can get molar concentration of NO-Br₂, which is equal to K1 into NO into Br₂. Let's substitute this value in equation 3. Rate will be equal to K1 into K2 into NO raised to the power 2 into Br₂ raised to the power 1. Or rate is equal to constant into constant is another constant represented by K into molar concentration of NO raised to the power 2 into Br₂ raised to the power 1. Usually we don't write 1. Hence the overall order of reaction is of third order. These facts clearly indicate that rate equation cannot be predicted from the stoichiometric coefficients of the balanced chemical reaction. Hence the rate law is determined experimentally. Fractional order reaction. The reaction of hydrogen plus bromine to form 2HBr is a fractional order reaction. Order is 1 with respect to hydrogen and half with respect to bromine. Negative order reactions are also possible. Sometimes the rate of reaction decreases as concentration of one of the constituents, means reactants or products, is increased. For example, transformation of ozone into oxygen, 2O3 is changing to 3 moles of O2. Minus half d of O3 divided by dt is equal to K into molar concentration of O3 raised to the power 2 divided by molar concentration of O2. So the rate of reaction will be equal to molar concentration of O3 raised to the power 2 into molar concentration of O2 raised to the power minus 1. The order of reaction with respect to oxygen is minus 1. That is why the rate of reaction decreases with the increase of concentration of oxygen. That is why this is an example of negative order of reaction with respect to oxygen. But overall rate of reaction is positive.